is the first of three models, hierarchical Bayesian models taken from Hobbs and Hooten. And what we're interested in is the fecundity of the northern spotted owl. And fecundity, we can think of that as the inherent ability to produce offspring. And so we've got data on 5 birds. Represent that as yi, and yi is the number of offspring, where I identifies the bird goes from 1 to 5. And one thing that's worth noting is that fecundity, the thing that we're interested in, is not the same as the number of offspring we observe. This thing, fecundity, is a latent variable. So what's a latent variable? Well, according to the folks at SAGE, a latent variable can't be observed. So we can't observe directly the fecundity of the bird, but we can detect it by its effect on something that is observable, which in this case is the number of offspring. So the latent variable and its proxy are not the same thing. Most constructs in research, according to these folks, are in fact latent variables. And so another example of a latent variable might be the scoring ability of an NHL player, something we'd want to know in order to figure out how much to pay them. So here we have 2 players. There's one, there's the other. Played similar number of games, scored the same number of goals, but the scoring ability might be quite different, even though they've scored the same number of goals, because they played for very different teams. So this dude played for a team that scored a lot of points. This fellow played for a team that wasn't quite as good. So it's very likely that even though the thing that we observed, the number of goals scored, was the same, their scoring ability might be quite different. And that's the same sort of thing here. Again, the whole idea is that what we're really interested in is the inherent ability of the bird to reproduce, but that's not necessarily, and wouldn't be in fact, the same as the number of observed offspring. Now what I want to do is go over the directed acyclic graph for the first model, and we will begin at the bottom as we always do, right there, where we have y, which is the number of offspring, and it's indexed by I, and I is going to go from 1 to 5 because we have 5 birds. And so those 5 values of y are deemed to have arisen as a random draw from a Poisson distribution that has parameter lambda, which is the bird specific fecundity. And this indexing of I is important because although this icon, we've got just a single icon here, but there are in fact 5 different Poisson distributions, 1 per bird. Continuing upward, these 5 different lambdas, the bird-specific fecundities, are deemed to have arisen as a random draw from a gamma distribution, and the gamma distribution is going to have a mean omega and a variance sigma squared. So if we think about it, if the 5 bird-specific fecundities arose from a gamma distribution with a mean given by omega, what does omega represent? Omega represents the mean fecundity of the northern spotted owl, and that's what we're interested in. To further go over this idea of a hierarchical model, it's useful to compare the hierarchical model with a non-hierarchical model, like this one, for example, we saw with the handedness experiment. So in the handedness experiment, recall that we had y is equal to 9 successes, where success was deemed as a person being right-handed. And those 9 successes were viewed to have arisen as a random draw from a binomial distribution with value theta, and theta is the probability that a randomly selected person would be right-handed, given that we polled 10 individuals. And we specified our prior for theta as a beta 4-2 distribution. So here's the comparison I want to make. In the non-hierarchical model, this prior for theta had fixed values of 4 and 2. In contrast, when we come over here, we've got our prior for the bird-specific lambdas is a gamma distribution. We don't fix with numbers, rather we represent those as symbols, omega and sigma squared, and then those omegas and the sigma squares in turn have their own priors. And so the difference from a practical point of view is that when RunJags goes on its random walk and does 10,000 iterations, in each one of those iterations, every iteration, this prior is kept constant as a beta 42. In contrast with the hierarchical model, in each one of these 10,000 iterations, these priors here, or we can think of them perhaps as hyperpriors, are going to be kept constant. But at each iteration, the values of omega and sigma squared are going to vary, and we're going to keep track of them, and at the end we're going to have posterior distributions of them. So what really matters is that ultimately, there's omega, there's the fecundity of the northern spotted owl, and we will have a posterior distribution of omega that reflects our belief about what is the true fecundity of the northern spotted owl. Next thing I want to talk about is the role that factorization plays in hierarchical models. So there's Bayes' theorem. The denominator is a constant, so we can get rid of it, replace it with a proportionality sign, and that gives us this. So what I'm going to do is I'm going to begin by substituting for this single parameter theta the parameters that are relevant to the fecundity study. So we're going to have these 5 values of lambda I, the bird-specific fecundities, omega and sigma squared, and for data, we're going to have the 5 numbers of observed offspring. So we're going to make those substitutions here and here as well. And then we're going to do factorization. And the first factorization is to take the joint probability of the lambdas, omega, and sigma squared, factor them out, partition them like this. And this ought not to be too strange, because if you think about the joint probability of a tree being aspen and tall, we can get that by taking the conditional probability of it being an aspen, given that it's tall, and multiply that by the marginal probability that the tree is tall. So if instead of aspen, we put in the lambda i's, and instead of tall, we put in the joint probability of omega and sigma squared, then this thing here is essentially this transformation here. Now comes what's really the critical bit, and that is we're going to keep this the same, but then what we're going to do is we're going to do this. So what we're saying is that the conditional probability of the y's given the lambdas, omega, and sigma squared, that can be reduced to the conditional probability of the y's given only the values of lambda. In other words, we're going to ignore the values of omega and sigma squared. Well, what permits us to do that? Well, if we come back up here, look at our model, like fair enough, the value of the lambdas, the fecundities, is dependent on omega and sigma squared. But once we've got this value of lambda, we no longer need these values of omega and sigma squared in order to arrive at our observed number of offspring. So another way to think about that, and this is from a fellow known as Clark, is say, okay, let's assume we're driving from Edmonton to Montreal. We could take this route. We could take, a different route like this. The whole point is, however, that once we're in Toronto, it doesn't really matter how we got there. And we're saying the same thing here, is that once we've got our value of lambda, how we got there, the values of omega, the values of the variance, they no longer are of importance. We can just think of the conditional probability of the values of y given the values of lambda. And in the final step, what we're going to do is we're going to say that this joint probability of omega and sigma squared, the mean and the variance, that can be partitioned into the product of the two. And the reason we can do that is we're going to assume that the mean and the variance are independent. And that should not come as a surprise either, because oftentimes when we think about the normal distribution with its mean and its variance, typically we assume that the mean and the variance are independent, and that's all that we're doing here. So, bottom line is, we start with these two things here, and by a factorization, we wind up with those 4 components there. And finally, I want to go over some terminology associated with hierarchical models. So here, of course, we have Bayes' theorem, and here we also have Bayes' theorem. But what we've done is we've substituted in the variables and parameters relevant to the fecundity experiment to the general variables and parameters shown in Bayes' theorem. And then finally, in this third line, what we've done is we've factorized this into its various components. And this factorization creates a bit of a problem, because initially with these 2 models here, everything is really simple. We can draw a line there, and these are the likelihoods, and these are the priors. So as long as we've just got 2 components, everything's really simple. But now what happens when we've got 1, 2, 3, 4 components, things get a bit tricky. And in fact, there is no consistent terminology for describing these different components. I'm just going to go over 3. So one possibility, and this is the one that mathematicians would tend to land on, is that we have a likelihood. There's a likelihood. We've got priors. There's priors. And then we've got hyperpriors. Those are the hyperpriors. Krushke comes up with something like this, where he's got the likelihood. There's the likelihood. Got the priors, but then he uses this term dependencies for this middle component, because what he's saying is that if we come down here, this value, the bird-specific fecundity, depends on the fecundity of the northern spotted owl and the variability among birds of that species. Another way, and this is the way that I sort of made up and kind of makes sense to me, is that we've got data processes, we've got phenomenal processes, and we've got priors and parameters. Now, first of all, this idea of phenomenal processes, this word phenomenal is just ugly. So if you're a biologist, think of those as biological processes. If you're an economist, think of them as economics processes. If you're a sociologist, think of them as sociological processes. So these are just the underlying processes that are likely to be our primary concern. And so what we're doing here is we're partitioning out the process that gave rise to the data as captured in the likelihood function from the biological processes. Now, in the case of a simple model like this, the distinction between this component and this component isn't that important. However, when we get to Model 3, we will see more starkly the significance of this partitioning. And then we've got priors and parameters. So if we think about the mean and the variance of the gamma distribution from which the individual bird-specific fecundities are drawn, they're going to need to have priors. So you're going to have a prior there for omega. You're going to have a prior there for sigma squared. But these values of omega and variance also appear on the other side of the proportionality sign. And we can think of those as parameters, and they're going to be the object of interest. And in particular, what we're going to be interested in is omega. So if one were to do a study as exemplified by the first model, the significant figure in the paper would have the posterior distribution of omega, where omega is the fecundity of the northern spotted owl, and this distribution would reflect our beliefs about the fecundity of the northern spotted owl.